So let's now consider a special case. So a special case of a spring. So let's imagine we have a spring and we have a little mass here, and we use that mass, we exert a force, and we squeeze the spring. So now the spring has been squeezed, and we let go. So the spring is going to unsqueeze, and when it's all the way unsqueezed, that mass comes off, and it's going to move at some velocity v. And so I want to know what is that velocity v, because as the spring was unsqueezing, it was pushing on it. And so that's going to be pretty straightforward. The spring is going to do work on the mass. And so a couple of things you're going to need to know here about the spring and the mass. We're going to say that the mass is going to be 25 grams. We're going to say that we squeeze it a distance of 14.3 centimeters. And the spring has a spring constant of 95.4 newtons per meter. Now let me explain the spring constant. Okay, so we've got a spring, and we'll discover later on this semester, we're going to derive how all this works. That is, if you compress the spring a distance x, it pushes back. And so the force is proportionate to x. And so if you squeeze at a certain distance, it pushes back by a certain force. You squeeze it twice as far, it pushes back twice as hard. Squeeze it 3 times as far, it pushes back 3 times as hard. And so it's proportionate. That proportionality is that spring constant right there. In particular, we normally say that the force is equal and opposite of x. So if x is pushing to the left, the force is pushing to the right. This is called Hooke's law. I hate just giving you an equation. Your book is bad about that. Most physics books are bad about this. Just throw out an equation, say, here's an equation, how things work. I like to explain where the equation comes from and so forth. I kind of motivated it here by explaining how springs, push back twice as hard, you push them twice as much, so that it's linear, but I didn't prove it. We will prove it later on the semester. We actually are going to derive this equation later on in the semester, but that's still a few weeks away. So for right now, just bear with me and accept Hooke's law. But that means it is variable. So that means that as this spring is decompressing, it's changing the amount of force pushing on the mass. So now the force pushing on the mass does work on it. So the work due to the spring is going to be the change in energy of the mass. Well, that's going to be the change in the kinetic energy of the mass. Okay. And so the work done by the spring is going to be change of the kinetic energy of the mass. So what is the work done by the spring? Well, that's going to be the integral of the minus kx going from the initial to the final position. Okay, dx. Okay, because the work is going to be integral f dx. Okay, so that means this is minus k integral x dx from initials how far it was squeezed, to the final is 0. So that means this comes out to be 1/2 kx squared. Okay, so the work done by the spring, 1/2 kx squared. Okay, well, that's going to equal the change in kinetic energy. So 1/2 kx squared is going to equal 1/2 mv squared. So the 1/2s cancel, and so the v is going to come out to be x times the square root of k over m. So that's going to be equal to 0.143 meters times the square root of 95.4 newtons per meter divided by m, which was 0.025 kilograms. So the velocity comes out to be 8.83 meters per second. Well, we can actually go beyond this, because what happened was, notice what happened. We squeezed the spring. Now, when we squeezed the spring, what happened was we had to do work to squeeze the spring. How much work did it take to squeeze the spring? Well, as we did that, we had to exert a force this way, okay, as it was moving that way. The force that we exerted was equal to kx, because the spring was pushing back with minus kx. So we have to do equal and opposite. That is Newton's third law. Okay, remember, Newton's laws apply. So we have to remember Newton's third law. So kx is what we did to it. Okay, so the work that we did to it was the integral kx dx, in which we started at 0 and ended at x. So when you do that integral, what you get is 1/2 kx squared. Now, this was the work done on the spring when we squeezed it. So when we squeezed the spring, that was the work that we did on it. Well, notice, what work did the spring do when it was unsqueezed? So the work done by the spring was 1/2 kx squared. So the work done on the spring ultimately was the same work done by the spring. Now, what does that mean? It means in some way, when we did work on the spring, we were putting energy into the spring. So the energy was being stored in the spring.